Professor Harrison, and welcome back to our module on probability for finance. Today we're going to be covering conditional expectations, what it means to take an expected value when you already have some information, and a powerful result called the law of iterated expectations, which turns out to be the foundation of how serious forecasting actually gets done. We're following Danny, a gambler with a mountain of debt, working his way through a box of mysterious letters addressed to his late father, trying to understand what happened to the family fortune. Today he's sitting with a question he can't stop circling. What can he actually expect to recover from the estate? He's been treating it as a single unknown number. The letter is about to change how he thinks about that. He opens up another one of those mysterious letters. Consider a cyclical industry company, the kind whose earnings move up and down with the broader economy. You want to set a price target before an upcoming earnings call. You could compute the expected earnings the straightforward way, list every possible outcome, assign probabilities, and take the weighted average. That gives you the expected value of the earnings per share, the unconditional expected value. But here's the thing, you're not completely uninformed. You know something about the current state of the economy. The question is whether you're going to use that information or ignore it. Conditional expectations are what happens when you use this information to inform your decisions. A conditional expectation is the expected value of a random variable computed given that you already know the value of some other variable. Instead of computing the expected value of x across the full sample space, you compute the expected value of x restricted to the part of the sample space that's consistent with what you know. The notation is written e of x given y equals lowercase y. The vertical bar reads given, and y is the specific value that you're conditioning on. If that structure sounds familiar, it should. You've already seen conditional probability, which asks, given that one event occurred, what is the probability of another? Conditional expectation is the same idea. We've just extended it from probabilities to averages. You're working in a restricted slice of the sample space, just the outcomes where the conditioning variable takes the value you care about, and computing the average within that slice. Going back to our cyclical company, suppose the macroeconomic environment is one of three different possible states: an expansion state, a neutral state, or a contraction state. Analysts have assigned probabilities of 50% to expansion, 30% to neutral, and 20% to contraction. And for each state, they've estimated a conditional expected earnings per share of $12 in expansion, $7 in the neutral state, and $2 in the contraction state. Each of those three figures is a conditional expectation. The $12 is the expected value of the earnings given that we know we're in an expansion state. The $7 will be the value expected of earnings if we know that we're in a neutral state, and $2 is the expected value given we're in a contraction state. They're different because earnings behave differently depending on what the economic environment looks like that the company is operating in. At this point, you have three scenario-specific forecasts. If you somehow knew for certain that expansion was coming, then $12 is going to be your number. If you knew contraction was coming, then $2 would be your number, but you don't know. You have probabilities, 50%, 30%, and 20%, and you have a conditional estimate for each state. The question is, what do you do with these to figure out what your true expectations actually are? This is where we get to the law of iterated expectations. The law of iterated expectations says that the unconditional value of x equals the probability-weighted sum of the conditional expected values of x, taken across all possible values of the conditioning variable. In words, for every state of the conditioning variable, take the conditional expectation of x in that state and multiply it by the probability that that state occurs. Then we add the results together. If we do that across all our states, we end up with the expected value of x, the full unconditional expected value. So for our cyclical company, the expected value of the earnings per share is going to be equal to 0.5 times 12, the probability and value of x in the expansion state, plus 0.3 times 7, the probability and value of x in the neutral state, plus 0.2 times 2, the probability and value of x in a contraction state. That works out to 6 plus 2.1 plus 0.4, or a total of 8.5. That 8.5 is the unconditional expected earnings per share, the same number you'd get if you computed the expected value of earnings directly from scratch without any conditioning at all. The law of iterated expectations guarantees that. Conditioning on a variable and then averaging back out gives you exactly the unconditional expectation. You haven't changed the answer, you've found a structured way to compute it. The intuition here maps directly onto something that you've already seen, the law of total probability, which you worked through earlier in this module. It basically says that you can recover an unconditional probability by conditioning on a partition of the sample space and weighting on each conditional probability by the size of the partition. The law of iterated expectations is the exact same structure, applied to the expected values instead of probabilities. The conditioning variable partitions the sample space. You compute the expectation within each piece, and you weight the probability of each piece and then sum them up. The reason these two tools end up being so important in practice is that analysts almost never work from a single unconditional forecast. They work in scenarios. What's the expected value if rates stay elevated? What's the expected earnings if the credit environment tightens? What is the target price if macro conditions deteriorate? Each of those questions is a conditional expectation. Each one conditions on a specific state of some variable that you care about. Rates, credit spreads, macro regimes, whatever the relevant driver is for your situation. You compute a conditional estimate within each scenario, you assign probabilities to these scenarios, and then you could use the law of iterated expectations to pull back everything into just a single number. That structure, enumerating over the relevant states and assigning probabilities of each before computing the expected value of x conditional on each state, weight and sum, is scenario analysis. That's how price targets get set before earnings calls. It's how credit analysts build expected loss models. It's basically the standard framework for any forward-looking estimate under uncertainty. And the law of iterated expectations is the mathematical guarantee that this framework is internally consistent, that your scenario forecasts actually add up to an unconditional expectation you can defend. Danny puts down the letter. He's been thinking about the estate as a single blurry number, some amount he might end up with somewhere between nothing and something. He's been applying rough expected value thinking, but without any structure. Just a vague average across a vague range of outcomes. But the letter reframes it. The expected value of what he recovers from his father's estate isn't independent of everything else going on. It depends entirely on one thing, whether the fund turns out to be solvent or insolvent during the proceedings close. So he conditions on it. He puts the probability that the fund is going to be solvent at around 40%. In this state, his expected recovery after all the fees and creditors he's going to have to pay is around $180,000. If things are insolvent around 60% of the time, that number drops to around only $20,000. The expected value of his father's estate ends up being very different, conditional on whether the fund ends up being solvent or insolvent. So Danny applies the law of iterated expectations. His unconditional expected recovery is 0.4 times 180,000 plus 0.6 times 20,000. That works out to $84,000. That number is useful, but it's not actually what changes his thinking. What changes his thinking is the gap, $180,000 on one side of the solvency question and $20,000 on the other. That one binary condition is doing almost all of the work. Every decision he's been vaguely circling, whether to accept a fast settlement, whether to pay for a forensic accounting review, and whether to contest anything, those decisions look completely different depending on which side of that conditional you end up on. The conditional expectations told him where to focus, and he's decided that he's going to push for solvency as the primary driver of being able to be successful in solving the issues with his father's estate and his own gambling problems. So that's the conditional expectation and the law of iterated expectations. A conditional expectation is the expected value of a variable computed within the part of the sample space where some other variable takes a specific value. You're working with the information that you have, basically. The law of iterated expectations says you can always recover the unconditional expectation by weighting each conditional expectation by the probability of the condition that it belongs to. What these two tools give you is the core of scenario-based forecasting, a disciplined way to build conditional estimates for every relevant state of the world and reassemble them into a single expected value that you can actually use.